All right, guys, let's go over this homework. We had a worksheet. It was 1 through 14, and it was assigned on, what was that, Tuesday, and it was due Wednesday, yesterday by 3:30. So what we're dealing with is simplifying radicals. So I'm sure you guys have probably done the other homework by now, but the reason why this is relevant is because when when we're using Pythagorean theorem, we're going to have to deal with radicals, and we're going to have to know how to simplify them. So let's just head right into this, okay? We were doing 1 through 14. So I'll just copy these over onto my, as we're going through them, I'll copy them over onto my sheet. So the first one that we have with number 1, do I need to make that bigger? Let me see how that'll look. All right, let's go with it for a minute, see how things work out. All right, so number 1, I have this square root or radical 150. We can say square root or we can say radical 150. Now, as Ms. Lovingood had told us, when we are dealing with these, we need to really make our factor trees. So what we have to think about, the most important thing to think about is when we're doing this is how to get started. Now, if I were to do a factor tree, all right, and let's say when you have an even number like 150, you can always start with 2. So that's going to be 2 times 75. All right, then there's nothing else I can do with 2. So now I break this down. Anything that's divisible, anything that has a 5 or a 0 is divisible by 5. So I can go 2 it's not 2, I'm sorry. Divisible by 5, I said, all right? So 5 goes into 75 15 times. 15 breaks down to 3 times 5. And then there's nothing else that I can do, okay? So we always want to look for the pairs. Whenever I have a pair, I can pull them out. All right, so I have a pair of 5s. Now, the pair comes out as 1, 5. All right, don't multiply them back together. And what am I left with? My prime numbers that would stay underneath the radical would be 2 times 3, or 6. Okay. Now, I can always go with 2s. I can always think about 5s when I have a number that ends in 0 or 5. But the one thing that we want to think about, guys, when we're doing this, if I have 150, all right, I like to think about my perfect square numbers. So perfect square numbers are 1, 4, 9, 16, 25, 36. Did I forget any? 49. All right. So this is really going to help me make this process when I'm doing my factor tree a little bit easier. All right. So let me demonstrate what I mean. If I realize that 150, it's like I have $1.50, how many quarters would I have? I would have 6 quarters, right? All right. So if I can break that down in using a perfect square, all right, and when I have 25s and 50s and 100s, I always need to think of 25 because it would just be like 4 quarters and $1. I can break things down, or 175 or 200, $2. All right. This would be 6 times 25, and then this is a perfect square. So right there, I know that that's a perfect square, which would break down to 5 and 5. That would come out as a pair, and I would have 5 radical 6. So I got to the same place, and this will become more important as we deal with larger numbers, okay? But I always want to look for perfect square numbers that I can use as one of my factors. As soon as I get it, I know that I can pull that out. okay? So what this is really saying, I could say if I have radical, well, I'll just do it over here. If I have radical 150, okay, then I can say that I have, after I do my factor tree, I could say I have radical 6 times radical 25. Radical 25 is going to be, just turn out to be 5. So now I have radical 6 times 5, and it's 5 radical 6. So once you do, I kind of went through 3 different approaches. I can break down my factor tree and then present it like that. I can make sure that I'm picking out my perfect squares. All right, perfect squares, and I'm right here, and then it comes down to this. And I can always think of the factors that I pull out when I'm doing a factor tree as they're underneath a radical, like this is. So we see that this radical 6 is not going to break down to anything else. The factors are 2 and 3, that's not going to help me. But I see that radical 25, we know the square root of 25 is 5. So that kind of helps us to expedite that process. All right, hopefully that makes a little bit of sense. All right, to you. When I go through this, I'm going to continue to try to use perfect square numbers as I review this. Okay, if you're doing your whole factor tree, just make sure that you're pulling out your pairs as we go through it. So let's all right, let's move on to number 2. Let's see what number 2 had for us. Number 2, this was the square root of 80. So I'll do another one of these as if I'm breaking it down to the factor tree. All right. So if I have 80, I always know that it's divisible by 2. So 2 times 40. Then this is 2 times 20. This is 2 times 10. And this is 2 times 5. So I have my pairs. Here's a pair of 2s. Here's a pair of 2s. And I'm left with a 5. So my 2s come out, my 5 stays underneath the radical. My 2s come out. So this set of 2 gives me 1, 2, and this set of 2s give me another 2. And I'm always going to multiply those together. So my final answer for this one, 2 times 2 is 4, radical 5. There's a variety of different ways you could have chosen to do 80 as 8 times 10. Bigger numbers are great. 2 times 4, 2 times 2. And Miss Lovingood likes to bring that down. Okay. And that's the problem. As your trees get more involved, you can lose a number. It's very easy to lose a number. This one is 2 times 5. There's nothing else that I can do with this. All right. So I have a pair of 2s here. I have a pair of 2s here, and I have my 5 left underneath the radical. So there's my 5. one of the two. I have a 2 from that set. I have a 2 from this set. So again, same answer. There's multiple ways to go about this. Let's take a look at one final example for this one. Let's say I had 80 and I wanted to do what I was talking about in my beginning example, where I'm looking for a perfect square. Okay. Well, if I were looking for a perfect square, I can go right to 4 times 20. Okay. So this, if once I start to get good, I can tell that that's going to come out as a 2. And then I have 4 times 5, and this comes out is 2 times 2. So again, I end up with the 5 in the radical, and then a 2 times 2. And this is 4 radical 5. So it becomes increasingly important. Sorry, that was out of view. It becomes increasingly important to try to get those perfect squares as we go along. Then I don't have to do my tree. I know this 4 is going to come out as a 2. This 4 is going to come out as a 2. Okay. So we just have to practice and get comfortable with these. So there's 3 examples of getting the same problem. All right, we're warmed up now. Let's jump into number 3, which is a little bit more difficult. Number 3, whoa, holy mackerel. Pardon me. Number 3, 8 radical 2535. So what were we saying? When we have a number that ends in a 5, we can always, it'll always have a multiple of 5. So again, I'm going to pull this 2535 out to the side. Calculator are probably going to be a handy little tool here. Let me make this a little smaller because I think we're way too close to start to see the paper. All right. So if I have 2535 and I divide that by 5, that breaks down to 5 times 507. Okay, now let's take a look at 507. The 5, there's nothing else, there's no other factors that I can break that down to. Now let's take a look at 507. I don't know if there's anything that we can do with that. So I'm going to have to this is going to be a situation with these larger numbers. I'm going to have to kind of do a guess and check. So for this one, 507, it's not going to divide by 2. Let's try 3. Let's see if it divides by 3. All right, so it does divide evenly. Well, that's good. I didn't have to guess and check very much. So I'm going to have 3, and I have 169. Now, again, it's important to recognize these things. And if you don't, it's fine. You can continue to break things down. But 169 is going to be a perfect square. So on your, if you have a calculator that allows you to do square root, basic calculator should allow you to do that. All right. So if I want to take the square root of 169, I'm going to find out that that is 13. Okay. So this is going to break down to 13 times 13. Now, this is the part that's going to come out. This 13 is going to come out. Okay. The 5 and the 3 are staying inside. The 5 and the 3 are staying inside the radical. So let's jump back over to our original problem. Now, keeping our work organized, I have to realize, don't forget that there was originally an 8 outside of here. Okay? Before I came over here and started to work on my factor tree, I had an 8 on the outside of my radical. So let's not forget about the 8. Now, we have a pair of 13s that are going to come out. So that's going to come out, and that's going to be, so it's going to be 8 times 13. Now, what is left inside the radical is 5 and 3. So I have 5 times 3. All right, so this process is very important, that you're keeping track of your work, giving yourself enough room to work, and really being mindful of your prime numbers, your prime factorization, and pulling out your pairs. Also remembering that there was, if there's already a if there's already a term outside of your radical, we have to make sure we take that into consideration. So 5 times, this is going to stay a radical 15. And what is 8 times 13? $104. So the final answer is 104 radical 15. All righty, tough problem. Let's take a look at the next one. Number 4. Number 4 is 9 radical 490. Okay, so again, referring back to what I had mentioned at the beginning of the lesson, I always want to think about perfect squares. Okay, so I have 1, 4, 9, 16, 25, 36, 49. So that should tell me something, all right? It's going to make my life a lot easier. If I have 49 as a perfect square, then let's break this 490. Let's be very direct with what I'm trying to do here. If I have 490, that can break down as 49 times 10. Now 49 is breaking down to 7 and 7, and I managed to use this perfect square to my advantage. All right. So we're being very deliberate with trying to use these perfect square numbers. Now 10 breaks down to 2 and 5. Does that help me out at all? It does not. Okay. So this is going to remain underneath my radical. Again, keeping my work organized, I have to remember I had a term outside of the radical when I started. It was a 9. When I factored my radical, I had a pair of 7s for 49, 7 times 7. So that comes out times 7. And what were we left with underneath my radical? 2 times 5. 2 times 5 is 10. Alrighty, so 9 times 7, 63, radical 10. And that's my final answer for number 4. All right, try to pick up the pace a little bit here. Let's do number 5. Number 5 is 7 radical 200. That's awesome. I like this one. Keeping in mind perfect squares. All right. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Okay. So the bell should go off. Here's a great perfect square for me to use when I break this down. When I break down my 200, I can have 2 times 100, and 100 is 10 times 10. I had an existing term outside of my radical before I factored the radical 200, which was a 7. I'm pulling out, I have a pair of 10s, so times 10, and what's left underneath the radical was 2. So my final answer is 70 radical 2. I hope you're getting these as we go along. Alrighty. Number 6. Another crazy number. Number 6. 7 radical 1573. Well, first of all, let's check this out. And this is another good thing. When you start getting bigger numbers, it's always in your best interest before you do too much work is to make sure that 1573 for some reason isn't already a perfect square. It's probably not because this is the way they presented the problem to us, but what the heck. Second square root 1573. It is not a perfect square. All right, it's pretty darn close to 40 though. 1600, which would be a perfect square. All right, so where do I want to start? Well, again, guess and check. I have 1573 divided by 3. Nope. 1573 divided by 4. Nope. So what numbers are going to divide by 3? 1573 divided by, oh no. Nine? Nope. Nope. All right, so 1573, I guessed on 13. Again, this was guess and check, and it turns out to 121. So when I'm breaking down 1573 and doing my factor tree, I would have 13 and 121. 13 and 121. Now, again, it's helpful to know my perfect squares, of which 121 is a perfect square, which would be 11 times 11. Okay. So this is a pair. Now getting back over to my original problem, I had a term already outside of the radical, which is 7. I have a pair of 11s, so I have 11 that's going to come out. Then what stayed underneath the radical was lucky 13. Okay, so to finish this up, 7 times 11 is 77 radical 13. All right, another toughie. Remember, always try to go for perfect square numbers if you can. All right, I started to guess and check. I came up with 13, and that ended up working out. I don't know how you would know that 121 goes into it, but hey. All right, moving on to number 7, halfway home. All right, number 7. We have 15 radical 704. Well, I know how I'm going to approach this. I would start out, because it's an even number, it's a multiple of, it's going to have the factor 2, so it can be divided by 2. So 704 divided by 2 is 352. I'm gonna ride out 2 as my factor here. So divided by 2 is going to be 176. I can still continue with 2. 88. So 2 times 88. 2. Oh, no, I don't want to do any more 2s. What should I do now? I mean, I can go with 2s. It's not a problem. I can go 2 times 44. And then what does 44 break down to? Think about a perfect square. 4 times 11. Okay. And then this breaks down to 2 and 2. All right. So I have a pair of 2s. I have a pair of 2s. I have a pair of 2s. And I have an 11 left over. Sometimes you have to use that 2, and there's no problem in that. That's absolutely no problem to use those 2s all the way through. All right. Your factor tree is just gonna be longer, and you have to make sure that you keep your work neat and circle your pairs. So I had an existing term of 15 out front before I started my factor tree. Now I have this 2 is going to be pulled out. I have another 2 is going to be pulled out. And then I have another set of 2s that's going to be pulled out. And I was left with 11 underneath my radical. All right, here's my 11. There was no, that's a prime number, nowhere to go with that one. So what are we going to have here? 15 times 2 is 30. 30 times 2 is 60. 60 times 2 is 120. 120, radical 11. 15 times 2 times 2 times 2 equals 120. Final answer, number 8. We're on the home stretch here. We're over halfway. Number 8, 3, radical 245. All righty. So my 245, I know that there's going to be a 5 in there, guys. 5. So I'm going to have 245 divided by 5. Gives me 49. I love that. and 49 is a perfect square that breaks down to 7 and 7. Okay? Prime factorization. I had a term of 3 outside of my radical. Here's my pair of 7s that are coming out, or 1's coming out to represent the pair. Okay? And then I was left with 5 underneath my radical. So my final answer, 3 times 7 is 21, radical 5. I like that one. I got a nice perfect square on that one. All right, number 9er. Number 9, radical 5. Now let's take a look at these type of problems. Radical 5 times radical 20. Radical 5 times radical 20. Let's make sure that we multiply these together first. So if I have radical 5 times radical 20, that gives me, what's 5 times 20? Radical 100. Is 100 a perfect square? Yes, it is, Mr. Eustace, and it is 10. So the square root of 100 is 10. Final answer. Yeah, so anytime we have this situation where you can just multiply those together, just as if the radical is not there, all right, but we're keeping it under the radical. Let's take a look at number 10. All right, number 10. Number 0, no. Not starting back on 0 again. Number 10, we have 3 radical 3 times radical 18. Now, in the previous problem, we multiplied the radicals together. It's like multiplying like terms together, all right? So in this particular situation, we just always have to remember that in these type of problems, there's always a 1 out here, okay? We just don't put it there, just like we don't put 1 in front of a variable. So all I would need to do with this one is 3 times 1 is 3, okay? And then I'm going to do my radical 3 times radical 18. So I can simply do 3 times 18 is going to equal 54. So I have 3 radical 54. Now, I always have to reduce, I always have to simplify to lowest terms. So now I'm looking at 54. I can always start with 2, and that would be 2 times 27. 27 is going to break down to 3 times 9, and then 9 breaks down to 3 times 3. All right, Miss Lovingood likes to do these, and that's really a good habit to get into. I circle them as they happen, but you could forget your some factors, and you have to be careful of that. All right. So 54 breaks down to 2 times 3 times 3 times 3. I have a pair. They're going to come out. I had a term of 3 outside the radical already. My pair is going to come out. So there's my 3 to represent the couple. And then underneath, I had 2 and 3, 2 times 3. So to finish this up, I have 9 radical 6. So 3 radical 3 times radical 18 ends up being 9 radical 6. Number 11. Oh, this is helpful. Number 11. All right, let's take a look at this particular problem. And you all might be comfortable with what to do already. The previous problem gave me a little bit of a clue of what's going on. Now, in this particular situation, there would not be any issues whatsoever if you said radical 9 times radical 6 gives me radical 54. Then you took your 54 and you broke it down, all right, to 2 times 27, 3 times 9, 3 times 3, all right? Here I have a pair. That wouldn't be a problem. So you're going to pull out your 3 to the outside, and you're left with 2 times 3 on the inside, which is radical 6. Not a problem at all. If you recognize that square root of 9 is a perfect square, this would simply reduce to 3 times radical 6. So again, there's no problem with doing this work with your factor trees if you need to do it. This is a perfect square. Hopefully you recognize that, and then you're kind of done. It's just 3 times radical 6. All right, so it's just 3 radical 6. So either way, you guys see that? There's all kinds of different combinations. So just think about what you're doing as you're going into it. All right, now we have 12, 13, and 14. Number 12, simplifying radicals. All right, I have radical 7 times radical 14. Interesting. Okay, so if I take radical 7 times radical 14, I can just do 7 times 14. It gives me radical 98. All right, 98 breaks down. Do my factor tree. I can always start, it's an even number, so I can always start with 2. 2 times 49. I'm loving life here. All right, so cool. So this ends up being 2 times 49 is 98. Okay, that breaks down. 49 is a perfect square. So there's my pair, and I have my prime factorization. So that actually ends up being 7 radical 2. Alrighty, that one was a little bit of an easier one. All right, number 13, radical 20 times 5 radical 35. I'm just multiplying, guys. Remember, there's a 1 here. So I have 1 times 5 is 5, and then 20 times 35. $700. That's not too bad. All right. Now 700 is a nice number. We like 100, right? So this breaks down to 7 times 100. 100 is one of our perfect squares, which is 10 times 10. So there's my pair. Okay. Prime number. So I had a 5 outside already. I pull out a 10 from this pair. So here's my 10 representing that pair. And what stays underneath the radical is 7. So this is going to end up being 50 radical 7. All right, and finally number 14, and that'll finish up this homework review of simplifying radicals. Radical 14 times radical 6. 14 times 6, enter, is 84. So I have radical 84. 84 breaks down to 2 times 42. 42 breaks down to 2 times 21. And 21 breaks down to 3 times 7. All right. So where's my pair? Here's my pair. That comes to the outside. And this 3 and 7 really didn't help me much. That doesn't do anything. So really what I'm going to have underneath there. So here's my 2 comes to the outside. I had a pair of 2s. So here's my 2 that was pulled out to represent that pair. And then left inside the radical, I have 3 times 7, or again, 21. All right. All right, I hope this was helpful for you to review this. Make sure that you go back over this, compare your homework, see where you're making mistakes or where you're having troubles. And of course, if you need any help with anything, make sure you get in contact with us and we'll be able to help you. We have another homework review coming up with Pythagorean theorem, so we'll see you on that video.